starting the unit on matrix algebra. We start with definitions. Firstly, a matrix is an ordered rectangular array of numbers. So all the numbers are arranged in a rectangular format that has got a particular order. Note number 2, that we have arranged all the elements in a rectangular format. The first matrix has got 2 columns and 2 rows. The second matrix has got 3 columns and 2 rows. The next matrix has got 2 columns but 4 rows. And then the last one has got 1 row but 4 columns. Note that all we do is just to leave a space between the elements or entries of a matrix to separate the different columns. And therefore, we are able then to say if a matrix has got equal number of rows and columns, then the matrix is called a square matrix. The next definition is that of a zero matrix. Note that in order for a matrix to be a zero matrix, all the entries in that matrix have the value 0. And then we call a square matrix. Note that the first requirement, it must be square. If it is a square matrix with only diagonal entries as non-zero entries, all the other entries zeros, then we call that matrix a diagonal matrix. The first matrix has got 2 rows and 2 columns, and the only entries that we have is 3 and -3 on the main diagonal. The second one is a 3 by 3, and the last one is a 4 by 4. Okay, then we've got a 3 by 3 matrix, which is what I mean by that, is that it's got 3 rows and 3 columns, and the only non-zero entries are found on the main diagonal. Also here we've got 4 rows and 4 columns in this last matrix, and the only non-zero entries are found on the main diagonal, and zeros are everywhere else. And then we have what we call an identity matrix. Note also that it is a square matrix that has got equal number of rows and columns, and you only have ones on the main diagonal, and we've got zeros everywhere else. So once you have ones on the main diagonal and zeros everywhere else in any square matrix, note that that matrix is called an identity matrix. And then we come to the sizes or the order of given matrices. The first thing that we do is to specify the number of rows, and then thereafter the number of columns. So A, we say, is a 1 by 1 matrix because this entry 5 is found in the first column, first row. So you only have 1 row and 1 column for matrix A, and then matrix B has got 3 rows and 3 columns. Therefore, we say it is a 3 by 3 matrix. And then C has got 4 rows and 1 column. So it is a 4 by 1 matrix. Note, always we start by specifying the number of rows and then the number of columns. D has got 1 row and 4 columns, so we call it a 1 by 4 matrix. And then E has got 3 rows and 1, 2, 3, 4, 5 columns. So we say it is a 3 by 5 matrix. Now we come to specify particular entries in a matrix. We use double subscript notation so that the first subscript represents the row and the second subscript represents the column. Note that all the entries in the first row, they start with 1 because the first 1 represents the first row. And then A11 is found in the first column. That is why it's first row, first column. A12, first row, second column. And then A13, first row, third column. A23 is in the second row but third column. So we always start with specifying the row and then specifying the column. So we can find any particular entry in any matrix by using the double subscript notation. Now let's look at the example 1, where we were given A, which is the matrix with entries starting from 1 all the way to 9. And we're asked to find A11. A11 is the entry found in the first row, first column. So that means A11 is equal to 1. And then we go to B, A31. A31, that means third row, first column. So third row, first column entry is 7. And then C, which is A23. A23, second row, third column. So that means we are looking at 6. A32, third row, second column. So that means we are looking at 8. So A32 is equal to 8. A23 is equal to 6. A31 is equal to 7. And A11 is equal to 1. So the double subscript notation always helps us to designate a particular entry in a matrix. Now let's look at number 2, which is an application. We're given the inventory control here. Suppose that we've got 2 models that are being produced by a particular company, and these 2 models are produced in 4 factories. So you've got 4 factories producing 2 models of wireless telephones. And then in the matrix given, the number of units produced for each factory are given. And we know, we have been told that all the entries represents thousands of units. So we're asked to answer the questions. So note that we've got 2 models. So the first model is standard and the second model is deluxe. Here, the side, we have the factories, and we're told there are 4 factories. So we've got factory A, factory B, factory C, and factory D. and we're told the number of units produced by each factory. So how many standard models are produced by factory D? Standard, where? In D. So that means we're looking at 8. How many, let me go to C, how many deluxe models are produced by factory C? Deluxe, in which factory? C. Deluxe models in C, that means we're looking at 14. Then we can be able to answer D, at which factory where we find no deluxe models produced. That means we can see that it's B. And then we have B here, how many standard models are produced at factory A. Standard models in A, that means it's 16. Let's go to the next slide. Then we're introduced to the transpose of a matrix. We get the transpose of any matrix. Note that it's any matrix, so any matrix can be transposed only if we do the interchanging of rows and columns of the original matrix. Note here that I've given you matrix A to be 1, 3, 5 in the first row, 2, 4, 6 in the second row. So this is a 2 by 3 matrix. Then the transpose of A. Note we don't flip matrix A. We take the first row and make it the first column of the transpose. First row, first column. Second row, second column. Don't flip it. So that means because it was a 2 by 3 matrix, then the A transpose size becomes a 3 by 2 matrix, because what we did was to take each row of matrix A and we made it a column of matrix B, or what we will call A transpose. Once again, do not flip the matrix. Take each row and make it a column of the transpose. Because if you flip matrix A, then it would mean the first row would have been, the first column would have been 2, 4, 6, and the second column would have been 1, 3, 5. And that means the first row would have been 2, 1 instead of 1, 2. Once again, do not flip, but take each row and make it a column. So the first row was 1, 3, 5, it became the first column. Second row, 2, 4, 6, it became the second column. We now we're on definition 10, a square matrix. Note again, it must be square. We say it is symmetric if it is equal to its transpose. So if we've got A, after transposing it, you discover that A and A transpose are exactly equal, then we say that matrix is symmetric. Then we go to 11. Skew or skew symmetric matrices. We say a square matrix again is skew symmetric if the transpose of that matrix is equal to the negative of the original matrix. Please note the differences. Symmetric if the original matrix is equal to its transpose, and skew symmetric if A transpose is equal to the negative of the original matrix. And then the last definition, a square matrix. A, for it we can be able to calculate the trace. So that means if we want a trace of the square matrix A, it is just the sum of the entries on the main diagonal. That's it. You just add the entries on the main diagonal. Note that the matrix has to satisfy the condition that it must be a square matrix. So you cannot find the trace of a matrix that is not square. Now we come to operations on matrices. We'll start with equality. So firstly, we need to remember or to realize you can never say two matrices are equal unless they satisfy two conditions. Firstly, they must have the same size and the corresponding entries must be equal. So that means entries in the same position must be equal and the two matrices must have equal sizes. Then you can be able to say the two matrices are equal, right? So let's do some examples. Firstly, A, we've been given that we've got a 2 by 1 matrix equal to the 2 by 1 matrix. So same size, fine. Then we can be able to say x is equal to 2 and x plus y is equal to 5. And then we're able to solve x equal to 2 and x plus y equal to 5. That means y is equal to 5 minus 2, which is equal to 3. B, now both these matrices have got the same size again, 2 by 2 and a 2 by 2. Now, first condition has been met. Note we've been asked to find the unknowns. So the first thing you do, you check whether the entries in the same position are equal. So 3 and 3 equal, minus 1 and minus 1 equal, and 4 and 4 are equal. Therefore, you can be able to say 5 is equal to A. Let's go to C. First condition is met, equal sizes. But then guess what? We cannot be able to equate these two or to solve for x and y. Reason? Yes, 6 and 6, same position, they're equal. But x4 and 0 are not equal. So you can't continue. So the first thing, check the sizes, then check whether the entries in the same position are equal. So this one cannot be solved. It's impossible because the 4 is not equal to 0. That is your reason. Then we go to D. These two we cannot even attempt. Reason, they don't have the same size. Left hand side is a 2 by 2 matrix. On the right hand side we've got a 2 by 3 matrix. So these two cannot be solved. It's impossible to solve for x and y for D because of the sizes. Then we go to matrix addition and subtraction. Note that we can add or subtract two matrices if they have the same size. And in order for us to perform the difference or the sum of the two matrices, what we do is to add or subtract the corresponding entries. That means entries in the same position. Let's do some examples. Example A. These two matrices have got the same size. They are both 2 by 2 matrices, so therefore we can be able to add them. So that means we can be able to have a 2 by 2 matrix as well. as the answer. So we know that 2 plus minus 1, that gives us 1. 3 plus 7, that gives us 10. And minus 5 plus 5, that gives us 0. And 4 plus negative 2, that gives us 2. Then B, remember, we can only do subtraction or addition if the two matrices have the same size. So this is not possible, cannot be done, because the first matrix is a 2 by 3 matrix and the second matrix is a 2 by 2. So those two cannot be subtracted nor added. Then we go to C. We let S and T represent the sales in thousands of dollars for a company in 1991 and 1992. So we've been given the sales, S and T. All right. So now the question we are asked is, what is the combined sales in thousands of dollars for the company for the given years? All right. So we know S represents the sales in 1991 and T represents the sales in 1992. So now you are asked for the combined sales in the 2 years. So what do? All in all, we add. So we're looking for S plus T. And we realize that both matrices are 2 by 3 matrices. So therefore, we can add them. So can you work it out and see if we are going to be able to get the correct answers? Then we move on to scalar multiplication. Here we are supposed to find a product between a scalar and a matrix. Any size of a matrix. What you do, you multiply each entry in the given matrix by that particular scalar. So it means that the size of the matrix does not change. All you do is to multiply each entry in that matrix by that particular scalar, and then you get your answer. Now, I would like us to consider doing these examples. Calculate. For A, we're supposed to calculate 2 times A plus B. Remember, addition requires matrices to be having the same size, and then we add the corresponding entries. So that means now A has to be multiplied by 2. So according to scalar multiplication, each entry must be multiplied by 2. So it's 2 times -1 plus 7. So I believe that that first entry should be 5. 2 times 4, that's 8, plus 9, that's 17. 2 times 7, 14, minus 6, that's 8. 2 times 2, that's 4, plus 4, that's 8. 2 times -6, that gives us -12, minus 1, that's -13. 2 times 11, that's 22, minus 8, that's 14. So I'm hoping that you understand that each entry in A is multiplied by 2, and then thereafter you add your answer to the corresponding entry in B. So that means our answer for 2A plus B should also be a 2 by 3 matrix. Then we go to B. negative C minus A. Negative C minus A, the first thing you do, substitute C in. So negative C will be negative 3, negative 19, negative 7, and positive 5. Minus A as it is. Then you'll say it is impossible. Reason, these two do not have the same size. Remember, you cannot subtract nor add two matrices that do not have the same size. Then we go to C, which says B minus half A. B minus half A. Now that means you start with B. So you substitute. So what you do is to write out B as it is, minus half times A as it is, and then up to you whether you'll be able to do it by inspection or not. Another person would first multiply half to each of those entries and then thereafter do the subtraction. So you'll all get the same answer. Please do that and see whether you'll be able to get the same answers. Then we go to matrix multiplication, which is a bit complex compared to scalar multiplication. Firstly, let's go to the conditions that are attached to matrix multiplication. The first one given to us is that the number of columns in the first matrix must be equal to the number of rows in the second matrix. And before you can even start the multiplication process, that condition has to be met. Hoping that you realize these two matrices do not have to be having the same size. No. What is important is that the number of columns of the first matrix must be equal to the number of rows of the second matrix. Then the size of the product will be comprised of the number of rows of the first matrix and the number of columns of the second matrix. So it means we've got A, which is an M by P matrix. It's got M rows and P columns. You are multiplying that to B, which is a P by N matrix. P in B are the number of rows and N the number of columns. Then, because the number of columns of A and the number of rows of B are equal, then we can be able to say that AB will have the same size comprised of the number of columns of B and the number of rows of A. So let's quickly do some exercises. First example. Now, before we continue, we need to realize that a transpose of a matrix swaps around the columns and the rows. So if a matrix was a 2 by 3 matrix, then its transpose will be a 3 by 2 matrix. Let's remember that as we continue. And also, we need to remember that we cannot add or subtract matrices unless they have the same size. Also, we need to recall that matrix multiplication requires the number of columns of the first matrix be equal to the number of rows of the second matrix. As you do this, please recall those. And also remember lastly that when you multiply a matrix by a scalar, the size of that matrix does not change. Please recall those. So C times C transpose. We need to check whether it is possible. C is a 5 by 2 matrix. C transpose is a 2 by 5 matrix, because now you swap these two around. Then it means you will have a 5 by 2 times a 2 by 5. So let me try and write it here. 5 by 2 and a 2 by 5 matrix. So that means you have these two equal. So that means the product C and C transpose will have the size 5 by 5. Because those two are equal. Now we do the same for all these, for B, C, D, E, and F. Note B and A transpose. Is it possible? B is a 4 by 5. A transpose is a 5 by 4. Yes, it's possible. So B times A transpose will give us a 4 by 4 matrix, right? Minus 2 times C. C is a 5 by 2 matrix and it's multiplied by a scalar. Remember, a scalar does not change the size of a matrix. So 2 times matrix C will still be a 5 by 2. So B times A transpose gave us a 4 by 5 times a 5 by 4. So that means B times A transpose gave us a 4 by 4 minus 2 times C gave us a 5 by 2. So a 4 by 4 matrix minus a 5 by 2 matrix is impossible, because when you subtract two matrices, they must have the same size. Okay, now the negative of A times C. Firstly, can we multiply A and C? A is a 4 by 5, C is a 5 by 2. These two are possible. You will get a 4 by 2. But then there is a transpose here. Remember that negative does not change the size of that matrix. So you have a 4 by 2 transpose, so that means we have a 2 by 4 matrix for the first bracket of C. And then you've got a 2 by 4. 5 times D transpose. D transpose is a 2 by 4. And when you multiply that by 5, it does not change the size. So that means you've got a 2 by 4 plus a 2 by 4 matrix. It's possible the answer is a 2 by 4 matrix. I'm hoping that we are together on this one. Will be the final answer. Please make sure that you include all the steps. Can we add A and B? Yes, they've got the same size, 4 by 5. But a 4 by 5, can it be multiplied to a 3 by 4? 3 by 4 times a 4 by 5. Yes, 4 and 4 are equal. Then you'll have a 3 by 5 matrix. So please check and then do E and F and write the steps appropriately. Now, when we perform the matrix multiplication, remember the first condition still holds. The rows of the first matrix and columns of the last matrix will form the size of the product only if the columns of the first matrix and the rows of the second matrix are equal. So please make sure that that requirement is met before you continue. Then, to perform the specific multiplication, we need to remember, in order to get the entries of the matrix, the product matrix, we have Cij equal to Aik times Bkj. Now let's quickly go through the specific rows so that we get this right. Now here is my matrix A, and this is matrix B, and that is the product matrix, matrix C. Okay. Note, in order for me to get C11, I have to multiply the row of A by the column of B. So first row, first column gives me C11. In order for me to get C22, that means I must multiply the second row of A by the second column of B. Second row, second column, I get C22. Remember, 2 is for the row, the second 2 is for the column. So if you know your entries of the product matrix, remember C33. What does it mean? The first 3 stands for the row. So that means you've taken the third row of the first matrix and multiplied it to the third column of the second matrix. That's how you get C33. C13, that means the first 1 stands for the row. So that means you took the first row of the first matrix and multiplied that to the third column. So it was the first row and the third column. It's specified by the entry itself. So 1 stands for the row, 3 stands for the column. So that you don't make a mistake. So in the first matrix, you take the row. Second matrix, you always take the column. And note the specified entry that you are looking at. And remember, when you do the multiplication, you multiply the entries correspondingly and you add them. So that means when you multiply the first row and the third column, so that means the first entry times the first entry in the column, second entry in the row times the second entry in the column, third entry in the row times the third entry in the column, and you add them up. They will give you that entry which is in the first row, third column. Let's quickly do some specific examples so that we're able to see whether we're able to do this. Okay, firstly, with this one, this is a 2 by 2 matrix, and this one is a 2 by 1 matrix. So 2 by 2, 2 by 1, we can multiply 2 and 2 are equal, so we'll get a 2 by 1 matrix. That's the first thing you check, whether it is possible to do the multiplication. It's row, column. So this is the first column, first row, so that means I'll get C11. Second row, first column will give me C21. So 2 times 2, that's 4, plus 1 times -3. So that means I've got 1 as the answer. 2 times 7 is 14 minus 9. 14 minus 9, that gives us 5. Number 2, this is a 2 by 4 matrix, and this one is a 4 by 2 matrix. So that means you'll only get a 2 by 2 matrix. Please work out the entries. Remember, this is C11, C12, C21, C22. So to get C11, it's first row, first column. To get C12, it's first row, second column. To get C21, it's second row, first column. To get C22, it's second row, second column. So please continue to do this even for number 3, and make sure that you check your answers whether they are correct, and your additions as well. And you continue to do that for 4, 5, and 6, checking whether firstly it is possible to do those multiplications. The laws that apply to matrices, especially the few operations that we've dealt with, look at them: addition, associativity, commutativity. Please note number 5, AB is never equal to BA. Also note number 6, the transpose of the product of A and B will always be equal to B transpose times A transpose, and the transpose of a transpose gives you the original matrix. Please take note of these laws, and then we do the exercises. I need you to be specific. You go to a specific row and a specific column that has been asked for. Here we have AB, and we're asked for the first row of AB. Remember, first row of AB will have C11, C12, C13. So that means you are multiplying only first row of A to all 3 columns of B. And A is the first matrix and B is the second matrix. Note now, when you get to number 2, we are looking at the second column of BA. That means B is the first matrix and A is the second matrix. You can isolate a column or a particular row that you're talking about. Please note that B is the first matrix. So in B, we're taking rows. In A, we're taking columns. So when we're asked for the second column of BA, that means you're looking for C12, C22, and C32. Do that multiplication and see how you go about it. And then C is asking for the third row of A times A, and D is looking for the third column of B times B. Lastly, we're given matrices A, B, C, D, and E. You are asked to determine the trace. In A and D, you are asked for the trace. B and C, you are asked for you to do those specific operations. Please work on these exercises and see if you'll get everything right.